Okay. Good morning. So, two announcements. First, quiz 8 will be released after the lecture. It's actually ready. I have to just make it visible. So the deadline will be this Thursday, as always, at 11:30. So that's the first one. The second one is about the tutorial this week. So during the I will still hold the tutorial, and it would be sort of a Q&A. So if you guys have questions, if you want me to walk through parts of the Lab 4 code, we'll do that. So I'll still hold the tutorial, but I'll be just answering questions if there are any. So these are the two announcements I had. Okay, so if there are no questions, let's dive into the lecture. Oh, okay, so I have to bring the lectures. So the last topic we talked about last time was paged memory. We were walking through this example. So let's do that. Okay, so let's assume that you have 4-byte pages. So the first thing that you have to notice after you see 4-byte pages is how many bits of index do we need for 4-byte 4-byte pages? Well, you need to address 4 bytes within each page. That means that you need 2 bits. So we're going to use 2 bits of virtual memory address for offset, and the rest of it will be used for virtual page number. Now, let's say this is your physical memory layout, and this is your virtual memory layout. And then these are the bytes that you have in each virtual page. So virtual page 0 has A, B, C, and D in those 4 bytes, and so on and so forth. So let's do the translation using this table. So we're assuming that this is our table, our page table. So we want to use this page table to find how or where each one of these virtual pages are mapped. Okay, so to do this, let's translate address for A. So as I said, we need 2 bits for offset. So we're not going to touch the first 2 bits. We put them aside. We look at the rest of it, and we use that as a virtual page number. Now, this virtual page number is indicating 0. So we're going to go look at the virtual page number 0 in our table and see where it's mapped. So virtual page 0 is mapped to physical page 4. Now we get that 4 and we add it to the offset to get the physical memory address. So this is number 4, and then we just put the offsets to get our physical memory address. So that's where A is mapped, and then so on and so forth, because all the successive bytes in that page, they all differ in their offset. So here we just found where virtual page 0 is mapped. Let's do another one. Let's do it for E. Again, 2 bits of offset, we put it aside. Now the rest of the virtual address, we look at it and we interpret it as virtual page number. Now this virtual page number is virtual page number 1. We go to the table and we see that it's mapped to physical page 3. So we just have the 3 in red, and we just add the offset at the end, and this gives us a physical memory. And this is where virtual page 1 is mapped in physical memory, and so on and so forth. So if you are interested, you can actually do some other translations, see where, like, you can do any of these numbers that I have if you want. This slide helps you to do that translation. I'm not going to actually move deep into this. So the idea, a big picture, you have usually, not always, usually more virtual pages than physical pages. But that is not what we care. We just care about where each virtual page is mapped in physical memory. So there has to be a mapping from virtual pages to physical pages. And of course, if virtual memory is larger than physical memory, then you would assume that there are virtual pages that are not mapped to anything, so they're invalid. So that's where we use the invalid bit, indicating that this virtual page is not mapped yet. Okay, so what do we have in each page table entry? So we talked about page table. Now let's focus on each one of the entries. So the basic information that we wanted to have is to point to an actual physical page. So that's the first thing we want. We also wanted to have some information, as we saw, about the access that the program can have to that physical page. Like, is this a valid translation? If it is valid, then is it a read-only access, or write and read, or write-only, or whatever other accesses? So you also need some access permission bits. Now, if you look at different kinds of accesses that a program can have to each address in physical memory, you probably can focus on these 3: read, write, and execute. These are mainly the ones that you could think of. Now, if you have read, write, and execute access, this is usually, so here is the use case for any combination of these accesses. So I think the interesting ones, so if you have access to all of them, that would be like code or data. This usually has low security assurances, so it's not common to have this access, but still used. What is more common is to give read and write access without execute, and this is very common when you are dealing with data. So you have read and write, but you can't execute it. Or if you're talking about code, you usually have read and execute access without write access, because you usually don't want programs to alter their code. So they can read it and execute it. This is also very common. The other common access control is just read only for data. The data that you just want a user to read, you just grant them read access. Write execute is not applicable. So a piece of data that you don't have a read access and you can execute it and write to it is not used. Now, this write, just giving write access is actually used. You can basically look at the device folder in your lab starter code, and you will see many of the registers that we're using have just write-only access. So it's usually used when you're interacting with the device. So these are the command registers that are mapped to memory. So when we'll talk about this when we talk about I/O, but when you write to a particular memory location, if it is mapped to a particular device register, you're basically writing to that device and giving that device control commands. Now, this is a one-way communication. You can only give instructions. You can't read from that register. It doesn't have any meaning. And because that register is mapped to a memory location, so you don't want to read that memory location. You just want to write into that memory location. So again, this is also very common when you're dealing with devices. Now, without read and write and just execute, this is also not common, but it could be used. So if you want, to protect a piece of code from inspection, you can just give it execute command, execute access without reading it, so that the user can only execute that code without reading it. And without any permission, so no read, no write, no execute, this could be used for guards. If you remember, at the earlier in the course, we were talking about protecting threads from each other, which operating system usually doesn't do. But if they want to do, they could use these guards. So they can put, they can grant access, no access to the boundaries between the stacks. And if a thread overflows its stack, it necessarily has to do something with that memory location that it doesn't have any access to, and that raises exceptions and prevents user from overflowing. Although if you have a malicious user, they can just jump from that guard. But yeah, take it or leave it. This is something that could be used for catching illegal accesses. Okay, so now these permissions usually are used in different mechanisms. So other than really serving users, you can use these to do all sorts of management mechanisms in operating systems. So here are some examples, which we will talk about later on in the course. The first one is demand paging. Basically, it means that you want, as we mentioned, if you have limited physical memory and you want to share that memory between multiple processes, then you have to pick which virtual pages you have in your physical memory. And if your physical memory gets full, then you have to evict some pages back to the hard disk and bring new ones. So when you evict a virtual page from physical memory, then you can mark that as invalid, as we saw, as I actually mentioned. So the process of migrating a virtual page to physical memory, to hard disk and bringing it back, it's called demand paging. We'll actually talk about it later. The way it's implemented is by using this invalid bit in page table entry. The other one is copy on write. So this is one optimization that many Unix systems do. When you fork, right after the fork, the child has exact same memory layout than the parent. They even share code, looking at their virtual layout. So one naive approach is to, whenever you fork, you just copy the entire parent's virtual memory to the child, basically creating two copies of the same thing in physical memory. But that is not the best way to do this, because usually after some instructions, the child is going to execute a different code and you have to change everything. So a better way of doing this is to keep one copy in physical memory and make both parent and child to point their virtual addresses to the same physical memory. But this is not enough. You have to make both of them have only read access. You don't want to give them write access. The reason is the moment one of them wants to write, that means that you have to now create two copies. So if the child wants to write, you create a copy for the child, because each one of them now has to have different memory. So when they write, you create the copy. It could be that the child never writes and just executes at something different, so you never need to copy that address. So it's kind of like a lazy copy. You don't really do it. You wait to see what's happening later to make a decision. This is kind of like an optimization you can do. Okay, the last example that I have is zero fill on demand. So this is also something that operating systems do. Let's say in your memory management manager that you implemented in lab 1, you really don't do anything with memory, right? When somebody deallocates memory, you don't overwrite what is in memory if you want to allocate it again to someone else. And that has security risks. So let's say one application allocates memory, writes a private key in that memory, and then deallocates it. Now, you don't want that data to persist in memory because it could then be allocated to someone else, and then that someone else can read that private and secure data. The way it's done is by zeroing the memory every time the memory allocator allocates memory to any process. Now, this could be really expensive because you're writing 0 to a big chunk of memory depending on how large the requested memory is. One of the optimizations that you can do is zero fill on demand. So basically, when you allocate, you don't give the requester a read access. So the moment the requester wants to read that memory, it raises exception, and it says, "Oh, the process wants to read. What should you do? What do you want to do?" The operating system, and then at that point, operating system can write 0 in that memory location, right? So you basically postpone zeroing that memory until the process wants to really read it. It could well be that the process never reads and just writes to it, and you should be fine when it's writing. But if they read, then you can just fill it with zeros. Okay. Now, let's talk about memory sharing with paged memory, how we can share memory. It should be easy, right? We have alluded to how sharing could happen. So you have virtual pages and physical pages. Now, the question is, can I share physical pages between two processes? And the answer is yes, of course, why not? So you can actually make two different virtual pages in two different processes point to the same physical page, and that should be easy. So here is an example. So let's say I have process A, and this is the page table for process A, mapping virtual pages to physical pages with write or any permission and valid and invalid bits. Now I can actually I can now look at another process, let's say process B, and let's say this physical page 5, I want to share it between the two. All I need to do is to map the same physical page to have that physical page in both of these two guys' page table. So if I have physical page number 5 here and physical page number 5 here, and both of them are valid, that means that these two processes are sharing that physical page. Now, they could share this with the same virtual page number or different virtual page number. It doesn't really matter, right? So, for instance, one example that they would do the same virtual page number is when you fork, right? As I just mentioned, when, let's say you fork, both of them have the same virtual layout, virtual memory layout, because both of them are executing right after the fork, the same code. So, and then if we just keep one copy of the process in memory, so both of them are also using the same physical pages, so this mapping would be exact same. So it's kind of as if we copy the page table. The only thing that changes is these permissions, as I explained. We make all of the permissions to read only. And the moment any of them wants to write, we then create 2 copies in physical memory, and then we'll change the physical page numbers in one of them, and then change the permissions. Hopefully that explains one example. So that's one example where you have the same virtual page and the same physical page. Now, another example that you could have different virtual pages for the same physical page is, let's say, when you want to share a library. If you remember, shared libraries are allocated between heap and stack. So there was an empty space there that we said we'll use for to map shared libraries. Now, depending on the process, you could have different free regions in your virtual address space. So the same library could be mapped to different virtual pages in different processes. So in process 1, it could be mapped from address X to address Y. In process 2, it could be mapped from address Z to address Q, right? So different virtual addresses pointing to the same physical address, which is basically the shared library code. Now here is an example of that shows this mapping. So this is the page table, and the ones that are null are the invalid addresses that are not mapped. So as you can see, there are holes here in the virtual address space. These are the virtual pages that are not mapped yet. Now, so a few things. Just by looking at this, I'm using 3 bits for offset. This should tell you that each page is 2 to 3 bytes, which is basically 8 bytes. So the assumption here should be that each page is 8 bytes. Now, let's say that, yeah, I guess the other observation that you should have is these offset bits are going to just be copied here. So we just look at virtual page number to physical page number translation, and then we use the physical page number, we append it by the offset to get the physical address. Now, let's say you want to expand your stack. Let's say a stack is growing. And as of now, in this picture, the stack is not allocated. So the stack is allocated from address 1110000 to 11111111. Now let's say that the stack wants to grow. How do we do that? Well, the only thing that we have to do at this point is to allocate these virtual pages to physical page. Right now, if I look at the page table, these two entries are invalid, corresponding to these two pages. So all I need to do is to make these valid. So I find a free space in physical memory, and I just allocate it to this stack. So as you can see now, my stack has splitted because I didn't have enough space here to expand my stack, and it doesn't really matter. So I found some space in physical memory, and I just updated my page table with the new physical page numbers, and now everything is fine. So when the stack accesses the unallocated region, hardware raises exception, and that exception wakes up the exception handler in the operating system. Now, at that point, operating system has to make a decision. Is this an illegal access, or is this an access that I have to deal with? If it is illegal, if the program didn't have access to this and it was a wrong access, then you can just raise segmentation fault or page table fault. If it is something like this where the stack is growing, you can just update the page table and then tell the hardware to re-execute the program, the instruction that raised the exception. Again, I will talk about that in details about precise exceptions in later slides. Okay, so the downside of using page table is basically what you can see. Excuse me. Yeah, so the downside of paged memory, this naive way of paging, is that this page table can become quite large. So in essence, we need one entry per virtual page. Now, most of them will be invalid, as you can see in this example, or in real cases. Nobody's going to use all their virtual, I mean, barely they're going to use the entire virtual memory. So, but nevertheless, you have to have entries for each virtual page. Now let's see how big a page table could be in the next slide. So before getting there, actually, let's walk through some points. First of all, what do you need to do if you context switch between processes? Well, all you need to do is to change the page table pointer. So each process has its own page table in memory. Again, I'm reminding you of what I said in the last lecture, that compared to segment table, segment table was small because we have limited segments, and you can actually have it in physical in the processor. But page table, it's big, so you can't have possibly that much memory or that much registers. So you don't have any other options other than keeping your page table in memory. But then you need a pointer to the beginning of your page table. So that's the important thing. And whenever and that's something that the hardware should know about, as we will see next in next slides. But when you have a context switch, all you need to do is to update this pointer. So this pointer was pointing to this process's page table. Now that we're running this other one, it should be pointing to the other one. So now, how big is page table? Oh, thank you. How big is page table? Let's look at different settings because it actually depends on how big each page is. Now, let's look at a system, a 32-bit system with 4 kilobyte pages. Okay, now let's do some math. So 4 kilobyte pages, that means 12 bits. So we need 12 bits to address each byte within our page. So that would be the offset. So we will put 12 bits aside for offset. That gives us 20 bits, remaining 20 bits. So now we have 20 bits for virtual page number. So how many virtual pages do we have? 2 to 20 virtual pages. That's how many virtual pages we have, right? So our page table should have 2 to 20 entries. Let's say each entry is 32 bits or 4 byte. That basically amounts to 4 megabyte of memory. So it's not that bad. So each page table will be 4 megabyte, right? Roughly or exactly. Now let's look at a 64-bit system with the same page size. Now things actually going to blow up. So again, the size of the page is 4 kilobyte, and that would be 12 bits for each byte. So we put 12 bits aside. We're left with 52 bits. So how many entries do we need in our page table? 2 to 52 entries. Let's assume that each page table entry now is 8 bytes, and this makes sense, right? Because our address bus is 64-bit rather than 32 bits. Now, and then we know that we have to store the physical page number in the page table entry. So probably the page table entry should also be larger because now the address bus is larger. So let's assume that each one needs 8 byte, each page table entry. Now we have 2 to 52 entries, each one of them 8 bytes. That's 32 petabyte. Now, usually if you go and buy a system today, your physical memory is going to be at most like 64 gigabytes. Now, just one page table in a 64-bit system could be as large as 32 petabyte, right? So this doesn't make sense. Like now, my page table entry is bigger than my physical memory. Okay, so that's a problem. So now to summarize, the upsides of physical page memory, a paged memory is we have a simple memory allocation mechanism. As I mentioned, you can just store 0 and 1s to manage which pages have been allocated. It's also easy to share, as we saw. You just use the same numbers in the page table. Now, what are the downsides? It's inefficient if you have a sparse address space. A lot of entries are going to be invalid, and that's waste of memory, right? You're keeping all these entries in your page table, and 90% of them are invalid. So why are you keeping those entries to start with? But because of the limitations of the method, you have to have those entries and just keep them invalid. So it's inefficient. Along those lines, there are too many unused page table entries, and then if you have really small pages, then you have a lot of entries. So your page table becomes big. If you have big pages, to shrink your page table, if you choose to have bigger pages, like in this example, instead of like using 4 kilobyte, you might choose to have 4 megabyte pages. That brings down the size of your page table, but what it introduces is internal fragmentation, because now you're allocating these big pages to processes that might not need them, right? They might just use few bytes in a 4 megabyte page, and that's a lot of internal fragmentation. Now, to address these problems, we have to up our game. Excuse me. The way we're going to do that is by using trees instead of linked list. So if you think of it, page table is kind of like a linked list of all the entries. Now, to have a better one, we have to use a tree instead of a linked list. So that's like big picture. That's what's going to happen. So now we want to have layers of page table. And what is the idea behind having tree structure is, let's say my tree, the leaves of my tree are pages, my virtual pages. So I have as many leaves as I have virtual pages. Now, let's say a range of virtual pages are not used. They're invalid. So a range of leaves are invalid. Usually when that happens, you can actually find a root in your tree that covers most of these pages, right? So there is one root that covers most of these invalid pages, and there's another root that probably covers some other ones. So one way to do this is to just make those roots invalid without keeping any data for the leaves. So when that root is invalid, you don't need to store anything for the childs of that root. And that's how you actually save a lot of space, because for all the entries, all the invalid pages, all the invalid virtual pages that you have, you just summarize them in one root and make that one invalid instead of having to hold entries for each one of these virtual pages and making those entries invalid. So you make one entry invalid, and that indicates a lot of invalid virtual pages. So that's the idea. That's how we're going to save memory by using this 2-level page table structure. So let's dive deeper into how this is implemented. So similar to the original page table, so we're going to have a page table pointer. This is going to be pointing to the first level page. Now, each entry in my first level page table is going to point to another page table. So each entry is going to point to another table. So I'm going to use sum of bits in virtual address to address my first page table. Then I use some other bits to, and then other entries also point to other page tables. Now, once I find my page table that I'm interested in using the first bits, then I look at the next bits to index into my second level page table. And potentially here I have the translation. So here I can translate to a physical page number. So I have the physical page number stored in this entry. which I will use for physical page number. And then I just append it with this offset. And now I have my physical address. So this is my translation. So this now points to, so this entry points to a page, physical page, and this offset points to a particular byte in this page. So this is basically how we go around doing two-level page table. Now, here is the optimization. If all these white space here are invalid pages, invalid entries, I'm not holding any page table for these invalid entries. And that's how I'm actually saving space. So as long as they're invalid, they're not pointing to any other page table. And then because each one of those page tables inside each one of these now resides a virtual page number to physical page number translation that I don't need to hold. And that's how I'm saving space. Okay. Now, when I was walking through this example, I just said this many bits, first few bits, and then second few bits, and then offset. Now, these have to be fixed. How many of them, how many bits do we use for each one of the steps of translation depends on your page size and your page table size. Now, let's look at it. If you have 4 kilobyte pages, that means that you have to have 12 bits of offset that to address any byte inside your page. Now, let's say that each one of your page tables, second level page tables, let's say each one of them is 1 kilobyte. Let's say each one of them has 1024 entries. What does that mean? That means that you need 10 bits to index into that table. So that means that for virtual page number 2, you need 10 bits. Now the rest of it you're going to use for your first page table, right? So we started from putting aside the offset. Then we looked at the size of my the second level page table to find out how many bits we need to index into that. And then the rest of it, whatever is left, we'll use for the first page table or first level page table. Okay. And here is an example, right? So I have, in this example, I have code, data, heap, and stack regions. And then there are a lot of pages here that are not being used. Now, again, the assumption here is that each page is 8 byte. That's why I have 3 bits. Now, the assumption here is each second level page has 4 entries. What does that mean? That means that I have to put 2 bits aside for this to index into this. So I'm gonna having to have 2 bits reserved for page table number 2, and the rest of it I'm gonna use for page table number 1. So this basically means 3 bits for page table level 1, meaning that it has to have 8 entries, and then 2 bits for page table number 2, and then the rest of it is offset. And here you can actually see the translations. I look at the first 3 bits. It's 0, so I index into this table to find 0. And then I see that it's translated to the address of this page. Now I look at 00, So 00 is here. Now I have the physical page number. Now I just append it with 000 to get my 0001 0000 address in physical memory. Now the saving comes from these nulls here. So each one of these nulls, these are the roots that cover a lot of pages. In this case, each one of them covers 4, right? 4 translations. So by just having one null, I'm not storing any second level page table for this entry. And basically by doing that, I'm saving memory. So I'm not using that memory that we talked about in vanilla page table. Sorry, vanilla page table mechanism. Very similar. So if you want to expand your heap, you just go find this null here in second page table. Sorry, this was a translation. Then I guess I actually removed it. So I think there was another slide last term to expand this, to make this null, use one of these empty physical memories. So that's something you can do. So if you update it, it could be that you update a page table entry, a page table level 2 entry, or it might be that you have to use one here and create a new page table. Okay. So in best case scenario, where all of these guys are used, then the size of your page table, how much memory you're storing for your page table, should be roughly equal to the number of pages that your program is using. And because your program is usually using not all of its pages, that means that the size of page table is going to be limited. Okay, I got a question. What's the point of the 2-level page table? I'm having a hard time understanding how it saves memory. Let's see if I can use my iPad to explain it, but okay. I just figured out, I just got to know this technology a few days ago, so I'm using it now. Okay, so how does 2-level physical memory save us space? So let's say if you have 1-level page table, so this would be your page table. And then you would have as many entries here as your virtual. So this, how many entries? Number of virtual pages, right? So this is how big your page table should be. Excuse me. And then each one of them will point to a physical page. Now, many of them are going to be invalid because you have a lot more virtual pages than you have physical pages. But you still have to hold this entire page table, right? And just make them invalid, because at some point you might indeed use those virtual pages. So as we saw, the size of this page table becomes really big because you have a lot of virtual pages. Now, this was a flat representation of your this was a flat representation of your memory translation, and again, it's big because you have to have one entry per virtual page. Now let's see how 2-level or 3-level or whatever will save you space. Let's say I have all my, so let's say these are all my virtual pages. These are all my virtual pages. Now let's use let's break them to different page tables. So I'm going to put one, like some of them here, 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 right? And I'm breaking them into different pages, different page tables. Now I can put a page table here, first level. So I will make this second level. And I put a first level here. And each entry now here will point to the beginning of each one of these guys. Now here comes the beauty of this model. Let's say that these are invalid, right? Let's say some of these are invalid. In this model, I can just not have anything here. I don't store these pages, the invalid pages, and I just make these invalid here. So what I did was I did not store any memory here for these. No memory. No memory. I just here in this entry put an invalid. In these pages, in these entries, I put invalid. And I did not store any memory. Now compare this with this first model. In the first model, I still had to, so these are the ones that were invalid. I still had to keep memory for them and put invalid for each entry of them. But in this 2 model, I just put one invalid here and didn't have to save any memory here. So this is how I'm saving memory. So I'm keeping only pages for valid address translations, and the rest of them I'm holding no memory for them. So that's the idea. Oh, you guys cannot see my tablet? Oh gosh. All this time I'm explaining for nobody. Sorry about that. I thought I brought it to the, okay. Should have looked at the, Okay, so stop sharing. Share. I want to share the screen. Okay, now you should be seeing, right? Okay, so let me explain again. Sucks. Okay. Okay. In the page table model, you have a large page, and then you have a lot of entries. The size of this is the size of the number of your virtual pages. Okay, so the size of this is size of virtual pages. Now you might have a lot of invalid entries here. A lot of these could be invalid, not being used, right? So these are invalid, but nevertheless you're holding memory for them. And then some of them are actually valid. So the valid ones are pointing to corresponding physical memories. So you're still holding memory for all these invalid entries. Now, to move to a 2-level page, we come and we just partition this page table to multiple page tables. So I just partition them, the same page table. I'm just partitioning it to smaller pages, smaller page tables. Now, I could have invalid. I mean, I'm just, using the same example I had. So these are, some of them are valid. Some of them are invalid. Here I have valid bits, and then bunch of invalid bits here, right? So that's that. So all I do is I put another page table here. So this becomes my second level. And this becomes my first level. Now, each entry in first level is going to point to one of these page tables. Right? Now, what I can do is I can say, oh, this page table, all of it is invalid. So I don't store this. I just put an invalid here. I can do the same here. This one is also, all of them are invalid. I don't store it. I just put an invalid here. And the same here. All of them are invalid. I don't store it. I just put an invalid here. So as you can see, now I'm holding the only memory that I'm using are these 3 pages. The first level page table, which I always have to have, and these 2 that have valid entries. And all the invalid page tables disappeared. I just summarized them by just this invalid bit in the first level page table. So now you can compare here. I'm holding all the, I'm holding all of them, all of the entries. Here I'm holding only these 2. So hopefully that explains why this model saves us memory. Okay. Okay. Now we can actually combine segmentation and page tables to get something called multi-level address translation. So the idea is very similar to 2-level page table. Okay, that makes sense. Okay, good. So the idea is very similar to two-level page table. So now instead of having the first level page table pointing to second level page tables, we can use segmentation. So segmentation was a good idea to, to have segments in our virtual memory. And now we can divide each segment into pages. So basically you have your segment map or your segment table. So you use the first bits as segment number. You get a base which points to a page table. And then you have a bound. You check your bound with your virtual page number, and you use your virtual page number to index into this page table. And here you have your translation from virtual page number to physical page number, and the rest of the story should be familiar to you. And then you can also check the permissions and stuff. So in this model, what should you do every time you do a context switching? This page table hopefully resides in memory. This segment table could reside as we had it in the processor. So you just save the content of this segment table somewhere, maybe in your TCB or your PCB, and then you fill this table in your processor with new data for the context switched process. Now, how is it done in x86? This is just an example. So I guess we have seen all the different models of translation, from the simplest one, base and bound, then segmentation, then page tables, then multi-level page tables, and then segmented pages. So all of them you saw. Now let's see how it's actually used in reality. For one example here, I'm showing x86. So in x86, the idea is very similar to segmented page tables. So you have this global descriptor table, which is basically your segment table, that has pointer to page tables for each segment. It also has segment length, and it also has segment access permissions. And then as before, whenever you do a context switching, you just change this global descriptor. The registers in your global descriptor should be changed with the new process, and you just save that somewhere. This GDTR always points to global descriptor table. Okay, so I think in x86 model, I have to verify this. It feels like, based on my slides, I have to verify, sorry, but it feels like the global descriptor table resides in memory. You only have one register, which is this GDTR, that points to it. So you just change the pointer. It doesn't reside in the processor. I might be wrong, so I can verify this for you. But the idea is the same, right? Either you just have a pointer pointing to it, or you have it in processor, you use it. And then when it comes to page table, so you have the segment table. Now page table, instead of having only one level in x86, you have a segment table and multi-level page table. Let's look at it. So in 32-bit system, you have 2 levels of page table. In 64-bit system, you have 4 levels of page table. One thing I have to explain, which is kind of an unfortunate situation, the way I explained using segmentation and page tables is we use the first few bits of virtual address to index into our segment table. and then the next few bits for page tables, and then the offset to find the byte. In the x86 model, they decided that they don't want to use any bits from the virtual address to index into the segment table. Well, then you have to ask, okay, so how do you index into the segment table if you're not going to use any of the bits in your virtual address? And the answer is they introduced registers like stack segment, code segment, data segment registers. So every time a context switch happens, operating system sets the value of these registers, and the value of these registers are used to index into this segment table or global descriptor table. So basically in x86, I'm going to translate what I just said in pure English, is you're expanding your virtual address. So you're in a 32-bit system, it's as if you're adding some other bits to the beginning of your virtual address, which is basically those registers, because you're using those registers for your address translation to index into the segment table and then use the virtual address to index into your page tables. So it's kind of like a hack they did to expand virtual address. Now, in a 32-bit system, x86, they have two-level page table. So basically, this is a system with 4 kilobyte pages. So for 4 kilobyte, you're keeping 12 bits for the offset. That's 4 kilobyte, and then 10 bits to be used for first level page and second level page. In a 64-bit system, they have four levels of page table indirection. So instead of 2 levels, they have 4 levels. The other thing that you have to look here that I kind of alluded at the beginning of the term, in x86 systems, you basically are restricted to using addresses, bits from 0 to 47. So from 48 to 63, these bits are not used for address translation. So basically, you only have 48 bits to use for address, and the rest of them are just not used as of now. They're thinking of using them in future systems because the visual address seems to be expanding. But as of now, I think most of Linux and Unix systems don't use these bits. And so again, this is for a 4 kilobytes pages, so 12 bits for the offset, and then 9999 bits for each one of these middle guys. Okay, so let's do some interesting math. So each page is 4 kilobyte. Now, if I'm using 9 bits to index into 4th level page table, that means I have 2 to 9 entries here. Each entry is going to point to a 4 kilobyte page. So 2 to 9 times 4 kilobyte, that would be 2 megabyte. So this 4th level page basically covers 2 megabyte of memory. Now let's go one step further. Now, how much this guy, this page table covers. So it has, again, nine bits. That means that we have 2 to 9 entries. So 2 to 9 entry, and we just saw that each entry is a 4th level page, which covers 2 megabyte. So I can say each entry covers 2 megabyte. I have 2 to 9 times 2 megabyte. That's 1 gigabyte. So a 3rd level page covers 1 gigabyte of physical memory. And you can go actually up the ladder. So then here you would be covering 2 to 9, which is 512. So it would be 512 gigabyte. A 2nd level page covers. Now, why is this important? It becomes important if, let's say, you have used 1 gigabyte of consecutive bytes in your physical memory for, let's say, a file, or I guess code cannot be that big. Let's say for a file, you brought a file to your physical memory and you gave it consecutive bytes in your physical memory. And let's say it's 1 gigabyte. So the entire 1 gigabyte, let's say you want to give it to one process, it's just one file. What you can do is you can use the same idea we used for multi-level page table to save memory. You can actually disregard these two, this and this, so the 4th and the 3rd level, and just use this entry in your 2nd level to point to the beginning of this big 1 gigabyte. So you basically are saving, because all of them are consecutive, you don't really need this 4th level and 3rd level page for this particular address. So you can just use a super page, that's what it's called. You create a super page, which covers consecutive addresses in your physical memory, and you just save it with one entry in your page table. So again, if I'm just reading this, if physical memory covers a consecutive region, then you can just save memory by not saving the 4th level or 3rd level page tables. Now, this actually has another, it's not just saving memory here, it has another benefit for us, which is performance, which we will talk a lot about in the next lecture. So as of now, something in your mind should be alarming you right now. Bing, 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 bing. There is something wrong. I wanted to translate a virtual address to physical address. So let's say I wanted to read a byte in memory. I wanted to read 1 byte in physical memory. And for that, I had to translate virtual to physical memory, which is fine. Now, to read this 1 byte, how many times I'm reading from memory to just translate from virtual to physical? In this model in front of your eyes, I'm actually reading 5 times for that one read. So I have to first read my 1st level page table, this entry, then I have to read this entry, and then I have to read this entry, and eventually the byte that I'm interested in. So 5 reads to just translate and eventually read the byte that I was interested in. So 1 read became 5 reads. And reading from memory is expensive. It takes a lot of time to read from memory. So, and then how many times do we read from memory when you're executing your program? If you remember the first slides I had in this lecture, I said at least we're reading once for each instruction because we want to fetch that instruction from memory. So basically, what I'm saying is, as of now, with no optimization in place, for each instruction, I'm reading 5 times from memory. And that's so expensive. And if this was the case with our systems, the performance of our systems would really be bad, because for each instructions, we had to go 5 times to memory. Because it's not the case, you should know that, okay, there are optimizations that we're going to do to not read from memory 5 times for each address translation. And that would be the topic of next lecture, how to optimize this. But as of now, things should actually be very dark because it's kind of like really expensive to do the translation. Okay. So this is basically the page table entry for a 64-bit x86 system. Because I have this slide later on, I'm going to move on. Now I will come back to some of these entries. As you can see, like copy on write, we talked about it. Dirty bit and access bit, we're going to talk about it. Read, write, valid, the owner bit. So some of these should actually, as of now, look familiar to you. But again, I'll come back to it later. So some other points that we can make before ending this lecture is, well, with a multi-level address translation, you can either share individual pages, as we saw when I was talking about page table address translation, or you can actually share an entire segment. Let's say you could have a shared segment for your library, and then you can actually, by sharing in your page, in your segment map, you can share the entire segment by just using the same address for your page table for both of these two segments. Right? So basically, let's say in process A, library, like the C library, libc, is mapped to segment 1. In virtual address, in process B, it's mapped to segment 3. But then because we only have one copy of the library, we can actually have one page table for it, and then just map both of these two segments to the same page table. And now these two processes, they just have different segment numbers for the library, but the rest of the virtual address they would use will just be translated to somewhere inside that library. So we basically shared an entire segment between the two processes. Okay, I'm over time. See how many more slides do I have? Okay, I'll have to finish this in the next lecture. Yeah, okay. Thank you so much for those of you who attended the lecture and those of you who are going to watch this later on. Don't forget your quiz, and then again on Thursday I'll hold the tutorial to just answer questions that you might have for lab 4. So come ready if you have any questions, or if you want me to walk through the code we can do that. So thank you so much. Take care, be safe. Talk to you on Thursday.